Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Good morning, good afternoon, and good evening. Welcome to today's episode of AI for Good. My name is Jin Cui, and I work for ITU, the International Telecommunication Union, the United Nations specialized agency for information and communication technologies. It's my privilege to moderate today's session on AI for manufacturing. AI for Manufacturing is a webinar service co-organized by ITU and UNIDO. Let me introduce our speaker today, Professor Hui Wong, a professor and chair of Sustainable Manufacturing at KTH Institute of Technology, Sweden. He is also the director of Center of Excellence in Production Research, one of the 5 national strategic research centers at KTH Institute of Technology. In 2020 to 2021, he has served as the president of North American Manufacturing Research Institution of Society of Manufacturing Engineers, and he has also served as the chairman of Swedish Production Academy during 2018 to 2020. In 2020, he was elected one of the 20 most influential professors in smart manufacturing by Society of Manufacturing Engineers. Professor Wang's research interests are focused on real-time monitoring and control, human-robot collaboration, brain robotics, digital twin, cyber-physical and sustainable production systems. He has published 10 books, 15 conference proceedings, and 32 journal special issues. He has authored or co-authored more than 600 scientific articles in journals, books, and peer-reviewed conference proceedings in the above research areas. Now, let's welcome Professor Wang. Professor Wang, the floor is yours.
Thank you, Jin. Thank you for the introduction. So today, I wanted to use this time to introduce a topic on how AI will shape human-robot collaboration. On the screen, you can see this spinning logo. This spinning logo symbolizes human and robot work together. As introduced, my name is Hui Wong, where I work for KTH Royal Institute of Technology. I wanted to share today with you the following topics. The first is the background and the definition of a human-robot collaboration, or in short, HRC. HRC will appear frequently in my talk today. It represents human-robot collaboration. Related to HRC research, of course, we need to make sure that workers, humans, working together with the robot is in a safe environment. Active collision avoidance is the issue, and how to make it safe, of course, AI can help to make decisions. Next related topic is dynamic planning and job dispatching to the available resources, including humans and robots. Adaptive planning. After that is a control issue. Control, normally we use a pre-generated control code to control robot. In that fashion, the code are not adaptive, not flexible to the dynamic changes. It is better to use a programming-free approach, use a different modality to communicate with a robot. Following that, how to support human operators working together with a robot, provide the needed support both visually or in other modality. Those are the topic for today. Finally, I wanted to share with you some ongoing challenges and future research directions. First, the question normally we need to ask ourselves is why we need to have a human robot working together. In the past, automation has been around for many decades. The aim is to try to pick up the work from human being and do it in an effective way. Automation has its benefits, particularly from a productivity, efficiency perspective. However, it has a limitation. If we look at the final assembly line of automotive industry or in the aerospace industry, many of the final product assembly is still based on manual work by the human workers. The workload is high, repetitive work is not good for the health of human operators. This is the introduction, the needs for introducing the robot to help a human. From this array, from 482 SME, small, medium-sized enterprises, the response we received, the top one is a robot with integrated collision avoidance system. Safety is mostly important. Second on top is a robot with a programming for everyone. User-friendliness is mentioned here. And the third one on top of the wishes is a desktop plug and produce robot, also related to the user-friendliness. There's another one. SME companies want to use the robot as operators third hand. So this is another one. The color bar shows here, the color code represent different manufacturing sectors as illustrated here. From industry requirements, we can easily find the research requirement here as well. In the future, the key requirement is to make a production environment safe. The second one is a programming free for the operators. And the third one, plug and produce. Fourth one, user friendly. This has formulated the scope of today's talk. So I will go through the literature review in 4 different core areas. The first research area is active collision avoidance. Also shows the bottom R1. There's several subtopics covered in this area. The second research area is the dynamic task planning. The third one on top here is adaptive robot control. We should use a different modality, different method to communicate with the robot and ask the robot to do the desired job. The fourth one is mobile workers assistance or support to the operators. All those 4 different research areas need some information data from the bottom on the shop floor to support decision making. So in the center, we have a research area 5, smart sensor network. This will provide all the needed information for informed decision making. If you look at the color arrows here, it shows the information flow in different ways, whether it's auditory, visual, or haptic, from human to the robot, or from human to other systems. This different form is also illustrated at the bottom, use a color code. And we call this symbiotic communication between human and robots. Let's first look at the classification between human and robot. Once the two are putting together, there could be different relationship. This is compared against what data, information, resource, or process can be shared in the vertical axis. The first one is coexistence, second one interaction, third one cooperation, and the fourth one collaboration. Collaboration, especially here, can share many of the resources, direct contact, working task, resource, simultaneous process. Compared with others, cooperation do not really requires direct contact and working task. So cooperation can be done remotely, but for collaboration, mostly we need to be in a shared environment together with the robot. Then we need to understand the characteristic of HRC, especially in assembly. As I mentioned earlier, robot in this context is not to replace a human, but to assist human operators. Robot initially may not have needed skill set. So over time, robot can learn from experience of the operator. In this case, we can apply AI algorithm, receives information, use sensors from human operators, and those after learning can retrieve the data and convert it to knowledge after training, after conversion, after learning. And those knowledge will help robot to do the job better and better over time. This is a learning process. When human and robot work together, it is in a dynamic environment. In this dynamic environment, we cannot use a pre-generated code to control robot. Otherwise, everything is predefined. In a dynamic environment, robot need to respond to the human's requirements, the situation, the context. From another perspective, human need to control and communicate with the robot in different modalities. Naturally, we think we can talk to robot just like we talk to other teammate, or use sign language, use both hand language, sign language, or use a whole body sign language, communicate with the robot. Those signs need to be predefined, understandable by the system. And how to process the sign language and speeches that also rely on certain AI algorithm in order to improve the reliability. Haptic control is another way, but it is also possible to use brainwaves to control robot. When we use speech, we talk to a robot or use gestures to communicate with the robot. All those actions are controlled by human brain. If a brainwave can be retrieved, especially the embedded command, then we can pass the command directly to robot. This has some benefit, especially in a noisy environment. Speech may not be reliable, or when human operator is busy doing assembly tasks, there's no free hand to make gestures. Then we can use brainwaves. Or sometimes we can combine two or more modalities together to increase the reliability of the communication. The next aspect is the key properties of our human-robot collaborative assembly. Multiplicity is one of them. Human and a robot can work in one-to-one relationship, or can work many-to-many, or can team-to-team. The difference here is a team shares a common objective when working together with another team of robot. While many-to-many, each of them may have own objective, own goal. That's the difference. Also, collaboration depends on who initiated the collaboration. It could be robot active, could be human active, or supportive, indicative. There's different ways during collaboration. When both human and robot are active, they actively engaged in the assembly task, try to complete the work at the same time. Or The robot can be active and the human provide supervision, correction when needed, vice versa. Human can be mainly the assembly worker, and robot provide screwdrivers when needed, just like a nurse in a surgeon operation room. Now we can have this definition. What is symbiotic HRC? What is the symbiotic HRC systems? A system in this case needed to have the capability of self-learning. This self-learning especially applied to the robotic system, not for the human operator. Human operator, as a natural human, will have the self-learning capability already developed over time. But the system needed to have this capability to be empowered by AI. It also needed to have a real-time multimodal communication capability to understand the context. From recent history, we know several quite amazing achievements in the AI field. When AI is applied to Go game playing, Alphago stand out. Alphago was competed with Go game champion Lisedo of South Korea in 2016, and Alphago was created by DeepMind. This is a cloud computing issue. There's a number of different cloud servers located in the US. It is also a big data issue. In order to win the game, there are 30 million different moves. Computer or the AI algorithm can find the most appropriate steps every time that has the highest probability to win the game. However, for a human being, within seconds or a few minutes to search through this huge solution space, it is impossible. Behind this AlphaGo, there's reinforcement learning combined with Monte Carlo search and a deep neural network for decision making. And consider that's so many different CPUs and GPUs working together against one human being. This is sometimes we see the power of AI is a team of computers, a group of algorithms working together. Another example is AlphaGo Zero, learning from scratch from another AlphaGo Zero. After 3 days, AlphaGo Zero can reach the level of AlphaGo to defeat Lisedo. After 21 days, AlphaGo Zero can compete and win the game among 30 top players in the world. After 40 days, no one can compete, no human being can compete with AlphaGo Zero. Now let's look at the core research in HRC assembly. We have sensor data made available. The target is how to make working environment safe. Human operator is in a safe environment. This can be done through vision-based approach, mounting 3 cameras around this working environment. Then it is possible to detect the relative position between human and a robot. We wanted to consider the worst case. If there's impact, how much is impact and how can we reduce the impact? The impact can be measured by the kinetic energy governed by this equation. Here, m is the mass of a human and a robot. In reality, we cannot reduce the mass of a robot, cannot reduce the mass of a human either. Even for the movement of a human, we cannot really reduce or control. It's a free will. What we can do is regulate the relative movement of the robot. When the distance is getting smaller and smaller, closer to 0, we reduce the speed of a robot to 0. Then this kinetic energy goes to 0. There's no impact. If there's any impact, it's a human colleague on the robot, not the other way around. Then we consider the system is safe. Similar approach was reported 2 years earlier by my research group. And in this case, we retrieve the movement, the behavior of a robot by sensors, monitor the sensor, monitor the robot through 3D model, and put cameras around to monitor the robot, human. In this case, the point cloud of a human being can be retrieved, and the 3D point cloud is superimposed to the 3D environment. Then we can calculate the relative distance. That distance is used to control the behavior of a robot. And the processing is to the right-hand side. And here you can see a recorded demo. Without touching the robot will react, try to avoid a collision. To the right-hand side, you can see the colorful images on top. That's from 2 cameras with the depth information. The red is closer to the camera. The blue is further away. After removing the background information, we retrieve the humans from 2 cameras, integrate them together, get a 3D point cloud. And this is superimposed into one digital environment to do the calculation and control the robot. In order for assembly line or assembly cell to work properly, we also need to specify different safety policies. When human is approaching to the robot reach a certain threshold value, audio warning will be triggered. At the same time, the robot can reduce the speed to prepare for a sudden stop. The second safety policy is if this distance is getting even shorter, the robot will stop. The third case, the robot will move to the opposite direction in order to maintain sufficient safety distance, because the operator entering into the robotic cell with some purpose. Perhaps it's for quality checking or perhaps for adjusting the fixtures. We should respect this safety distance. The last safety policy is to dynamically modify the trajectory of a robot. Initially, it's a red straight line. Robot wanted to move along this line to the target. When human approach, the robot change trajectory. At all time, try to keep the safety distance. If this safety policy is combined with the assembly plan, the robot will have a different behavior when doing different assembly tasks. So here shows some of the examples of testing. Robot initially move from 0 to 1 and go to 2, try to move back to 1. But at this moment, human appeared. This red cross is a human hand. In order to maintain the safety distance, robot change trajectory, follow this dark circled 2 curved path back to 1. It is also possible to change the way robot is behaving. In this case, robot will follow human hand. Human hand follows this trajectory from 1, 2 to 3. And robot try to keep the same distance from the human hand and follow this dark circle to 1, 2, 3. That's another way to change robot behavior. Without the programming, robot can move. The second research topic is how to decide the assembly plan over time. There may be different scenarios that we need to consider. Along an assembly line, there may be different cases. In the first case, robot and human work on the different side of a car. There's no direct contact. There's no risk to the human being. In the second case, there's a mobile robot. This robot is used to transport components, parts, tools to the station. Once reach the destination, the robot remains stationary. There's no safety to the human as well, no safety risk. In the third case, robot and human work together simultaneously. So along this assembly line, there's different scenarios. Tasks need also to be considered when planned. Planning the task to be assigned to this case is a full human-robot collaboration. This needs to be considered, or some assistive separate operation. That's the task for dynamic planning and job dispatching. Machine learning can be applied to this to solve the problems, find the solutions. There's a number of different data information already available, can be retrieved by sensors or retrieved by robot controllers, retrieved from smart tools, or even from historical databases. The data at this stage remains just data, but after learning module, the data can be converted to knowledge. This knowledge, once applied to domain-specific modules, will convert them to proper actions for robot to take to help assembly, human assembly. Domain-specific modules includes how to recognize the assembly parts that human is holding, what human is doing right now, human activity recognition, what would be the trajectory of a human's movement in the next few seconds. All those are relevant questions that machine learning, deep learning can help. So this slide shows some result after training, how the video images captured can be analyzed properly to identify what part tools the human operator is holding, what assembly action the human is doing, installing, picking up a component, or just standing. So here is the result, calculated in real time with a high accuracy. And this is one example of how deep learning is applied. So moving forward, if we have a camera that can see the real situation, the video images is passed to image processing module to recognize human motion, parts, tools, and contact details. This will further help the robot to make decisions when and what that tool needed to be passed to whom. Of course, behind this, we can use a different machine learning algorithm or use a probability analysis. In this case, the actions and a component can be symbolized by different symbols, and there's a logic behind them. We check this probability from low order to high order eventually to maximize the logic. That gives you a different pair in sequence. When I pick up a screw, then robot will hand over a right screwdriver, either plus or minus. All those details can be done, can be retrieved from learning modules. So that's the objective. Another way to get context-aware trajectory planning is through learning from training. Initially, if I reach out my arm with a handband on the arm, and the trajectory can be captured through a camera or embedded sensor. Every time I reach out, there's a trajectory, and this can be done through a number of different times in order to capture all possible trajectory of a human in this case. We can teach robot by drag the end effector of a robot to the human hand for safely hand over the component, then every time you drag it over, that's the trajectory of a robot. This can also be done in multiple times in order to get sufficient data. This passed to the module to normalize both the human and robot trajectory, then we can create correlated model. In reality, during real-time inference, whenever human reach out, there's a trajectory that can be captured. From the correlated model, it is possible to identify the most appropriate robot trajectory. After the normalization, we have a real trajectory of a robot that can guarantee the component can be handed over to the human. So here's one recorded demo. You will observe that every time a human hand is at a different position, different height, and the robot can pass it over. And behind this, we use the recurrent neural network to do the calculation. This table summarizes some typical machine learning models. The popular ones that we used are summarized in red here. So the next research question needed to be addressed is multi-modal communication between human and the robot. There's a different way to realize this programming-free objective. We can use a gesture-based approach, or use a brainwave-driven approach, haptic-based approach, voice processing-based approach. Given the time limit, I will mostly focus on the top two. Regarding gestures, there are different types of gesture. Either it's an intended gesture or unintended gesture. For unintended gestures, we do not consider here. For intended gesture, it can be divided into communicative, manipulative. Manipulative is very straightforward for our human beings. Whether it's a pushing or it's a turning, by the action, we understand the meaning. This can be captured and communicated to robot. For communicative gestures, popular one is by pointing. We point one point in 3D space and draw a curve, draw a line. That's a 3D trajectory. Or can be a pose, different type of a pose, or pointing to a direction. The command in the middle, this command gesture, is based on symbolic. This is difficult for human to understand without domain knowledge. And this needs to be predefined. Once defined, then both the human and the system can understand, take needed action accordingly. So here's one example. Use pointing gestures to specify the point in 3D space by connecting the points together. That's robot trajectory. And use augmented reality, we can visualize those pointing trajectories and how robot follow it. It is also possible to use finger gestures to grab and drag the veer point in 3D space to modify the trajectory in real time. Without programming, robot can follow this new trajectory in 3D space. You may observe right now the accuracy is not high, and this is some future work to improve related to how to process the 3D gestures to increase the accuracy of algorithm. There's some work to be done in the future. We can also apply whole body gestures. In this case, because the robot is heavy, is big, risky, we ask the robot to stop by this gesture. Then human operator can safely do her job to mount a cable. Once this is done, she uses a different whole body trajectory gesture to tell robot, now it's your turn. And the robot will pick up the task from there and continue. This is another way of interacting with the robot. Use a brainwave to control robot is another modality, but it's also very challenging. When we silently think about a control command, our thinking can be captured by EEG signal, that's a brainwave, through multiple channels through electrode. The EEG signal, electroencephalography, can be passed on through the processing pipeline. Multiply the signal to make it stronger, retrieve them, remove the noise or artifact, retrieve, extract the features embedded in the multi-channel brainwaves, classify them, and eventually convert them to a function block. Function block with internal algorithm can further generate trajectory control command for the robot to move. So this is how brainwave can be converted to robot actions. However, there's a different type of brainwaves. The most useful one is shown here in blue text, the beta wave and the gamma wave, from 13 Hertz all the way to 100 Hertz. These are during the day when humans are awake and active engagement doing daily job. The other type is in sleeping mode or in meditation mode, may not be useful for daily work. Of course, then we need to have a system to integrate different pieces of information equipment devices together in a networked environment. As shown here, the sensor headset can be wear inside of a safety helmet, or in the future, the electrode can be embedded to the safety helmet. Operators need to wear it anyway during the work. That can automatically help us to retrieve human brainwaves, both for planning, control, and also for safety protection. We can think about once there's an alert or emergency panic situation, the panic will generate a high-frequency brainwave, and that brainwave is, if picked up properly, will trigger emergency stop of the nearest robot for safety protection. This, of course, needed to go through the pipeline of information processing, signal processing. I will not provide the details about this. However, if you are interested, there's a reference listed here for you to go through later. The pipeline is to analyze the brainwave, retrieve the hidden pattern inside from multiple channels, and then pass it on to function block to generate a control code. We call this also macro-micro control strategy. The brainwave signals or the brain-human control command is used to trigger the right function blocks, and the function block will tell robot how to do the job. If we want to visualize them, this is a topography map of a human on top view. Here's a nose, it's a ear. and the dots is a sensor electrode placement. At a different location of the brain, the strength of the signals are different over time. And the waveform from different channels is also illustrated to the right and the left. The macro-micro robot control strategy works like this. Because we cannot tell robot to move from left to right only by 10 centimeters or move in speed, certain speed. This very specific command is difficult to process. However, we can use the high-level command to trigger and select the right function block. For example, insert a pin. Then it will trigger the right function block. How to insert a pin is up to the function block to decide. It has several embedded algorithms inside to decide the position, trajectory, speed, acceleration, force, and so on in order to push the pin in. The behavior of the function block is governed by internal execution control chart or finite state machine to call the right algorithm. Eventually, as I mentioned earlier, the high-level control command will trigger the right function block chain in order to do the task to safely doing the assembly without collision. The last research topic I wanted to share with you is how to support operators. Normally, from a plan, we know what to do, but here we also need to figure out how to do. How to do can be visualized to support a human operator, either use virtual reality, VR, or augmented reality, AR, or use audio, video, or text. Different type of information can provide hint support to the human operators. In a central system, the planning and replanning is conducted. The result is sent either to human or to the robot to execute the task. At a certain time, feedback will be provided from both the robot and human. And here, operator use AR devices like a HoloLens to support and visualize the needed information support. Normally, VR is used for ergonomic design to decide the best gestures, positions that a human needs to do the job. Augmented reality can be used for real assembly operations. We can rely on a smartwatch to initiate this interaction with the augmented reality. Then on demand, we know right now we need to assemble this component and fashion 4 screws. That's one way to help human operator. It is also possible to visualize the trajectory of a robot as shown in the blue line. Then the operator knows where to stand in order to avoid a collision. Safety mostly is related to standard. There's a number of different standards, either European standard or international standard specified by ISO already established. However, these standards mainly for robot, safety of a robot, and human normally is outside of the fence for safety reasons, according to this standard. There is one standard under development. This is still a technical specification for human-robot collaboration. Until this is done, practicing human-robot collaborative assembly is not legally enforced in practical industry situation. Let's look at the different cases. Standard normally considers the worst case scenario. What if a robot hit a human? Or in another case, when the collision is happened and the human is partially confined in a space, or completely confined in a space, there's nowhere to escape, or human is jammed in a robot structure. In all cases, it may generate a secondary impact if the operator falls on the ground. Even so, there's a lot of challenges. This brain robotics does provide some opportunities. Through this brain and robot interaction, it is possible to monitor and control the robot through brainwaves. It is also possible to sense the engagement of a human being in task doing. If a human is tired, perhaps it is good to slow down the pace of robot assembly, or even give an operator a short break, or in a panic situation to trigger the emergency stop. However, the challenges, as mentioned here, it is also the accuracy, stability, and fine-grained control command. This is difficult for brain robotics. The brainwave is so complex. Even we blink our eyes, it generates interference with the brainwave. Everything is controlled by brain. If we wanted to control robot, sometimes may not be feasible if we're doing some other tasks simultaneously. How to separate the true control command from messy brainwave is a challenge in signal processing. Luckily, we have a different AI learning algorithm that can increase the reliability, accuracy, even in a noisy environment, noisy waveform. We can perhaps in the future use more advanced sensors, invasive one compared with a non-invasive one normally has a better quality in terms of sensor data, but this is not ethical at the moment. There are several future research directions. Standard is one of them. How we can contribute to standard development to make them realistic is a challenge. If the standard considers the worst scenario, the speed, the force limitation will make robot not cooperative to human, or is not productive, not efficient. Another one, how about if we apply digital twins to human-robot collaboration and let digital twin execute in advance to explore different scenarios, including safety issues. Then when human and robot work together, it's always practical, safe, and feasible. Sometimes emergency does happen. When emergency happens, how to bring it back to the normal operation, this mitigation plan is important. When we use AR glasses or goggles, over time, it generates mental stress. We feel headache, dizzy. How to develop mental stress-free devices is another challenge, or use a different way to display the augmented reality instead of goggles. Trust, how to build trust between human and robot. Because we trust, there's no absolutely safe system. We do not trust program, we do not trust the system, do not trust the robot, just in case. If we can properly analyze the brainwaves, we have another layer of protection, use brainwaves. When we are scared, we generate panic information, signals in brainwave. That could be a last resort to immediately shut down the robot or a machine for safety protection purpose. Now I would like to show you an all-in-one video to highlight how these different technologies, AI, can be combined together in a workable scenario.
To enhance the scope of robot applications in all industries, we need a new generation of intelligent robot systems that offer a truly symbiotic collaboration between human workers and robots. A system that not just guarantees the safety of human workers in a fenceless, dynamic and intuitive working environment, but also supports the worker by offering instructions and help according to the workflow. A truly collaborative robot system must also offer easy and intuitive tools for system interaction and robot control.
Symbiotic, show me the part.
Besides the collaborative aspects, a symbiotic robot system also needs simplified methods of robot programming, so that even non-expert users can easily create new program sequences or complex task planning, even for small lot sizes. Therefore, 15 research centers, universities and companies from all over Europe have joined forces in the Symbiotic Consortium to develop new solutions for a safe, robust and reliable human-robot collaboration.
The last piece of information is more for the future. We are in a period of considering Industry 5.0. In Industry 5.0, human centricity is highlighted as one of the pillars. We consider the future assembly could be human-centric in order to maintain the leadership position of a human being. But a human has some limitations in terms of physical strength. In this case, if we apply augmented robot like exoskeleton, it can energize the muscle power of a human being. We can also apply cognitive system to help human operator, advise the human operator the holistic situation to make a better decision. Sometimes our observation, our perception is based on direct sense. However, sometimes we cannot see something important. If we use augmented reality, we can see something is non-visible. Use a digital twin, we can predict and observe what would happen in the near future. Our brain has a limitation for computation in terms of computation power compared with other type of computers, and intelligence also has a limitation. However, we have a flexibility, we have adaptability. Combining artificial intelligence with human intelligence to have this co-intelligence is another way to make right decisions at the right time. Then we can use our thoughts to control the robot, to have a free hands to do the assembly by ourselves in a team. In this case, robot can provide the needed support based on the real-time feedback from the assembly situation. This human is empowered, and all the supported technology is to ease human task. Then this individual may need to work with other members to form a team, how to maximize the teamwork in smart factory to make it sustainable and resilient is the aim for the future research along this direction. To summarize, I talked today how to guarantee human environment is safe. Active collision avoidance is active research area. Adaptive planning, job dispatching, programming-free robot control, and in-situ support to the human operators, supported by a central smart sensor network. Those are the relevant research topics for today and even for the future. Thank you very much. I stop here and more than happy to answer your questions and participate in discussions. Thank you.
Thank you so much, Professor Wong. It's really an impressive and comprehensive lecture. Before opening the floor to the audience, I have some questions. And as you mentioned, machine learning and deep learning are used to transform data to knowledge. And we know deep learning model is utilized for human motion prediction in the scenario of collision avoidance and proactive assistance of robot to humans. And we also know that deep neural network training is a data-intensive computational process. And so could you please introduce more about data acquisition in your research? And is there any specific strategy to ensure the quality of training data? And thank you.
Yeah, this is a difficult question, especially for deep learning. It needs quite a lengthy of training sessions. Also, the training require large amount of data. If the amount of data is insufficient, the model will not behave well. The accuracy is low. In normal situation, we can collect quite a lot of data over time to train the model, which is offline is fine. But for some mission critical data, we do not have data, or we have a very limited data. Those data are related to the equipment failure or fatal accident. Those data is not easy to retrieve. Otherwise, it's not ethical to put someone in a situation just for the sake of data collection. One approach, perhaps we can consider transfer learning. For example, for image processing, there's a huge image net, lots of data already available. I showed you one example in this presentation. We use VGG16 to process image data, which is converted from human brainwave. And that is one approach to use transfer learning. We do not need a whole bunch of data, but use an existing pre-trained model, VGG16, and then plus our own data. This is one approach, largely reduce the time for training. Another approach we suggest is a progressive training. During actual operation, it is possible to collect the data as well because the headset is variable. Data is collected at all time, and during real-time, real-world application, we collect the data and feed those data back to the model. For example, 5% of the data is new for progressive training. But this cannot guarantee initially we have an accurate model, but the model can be continuously improved over time. That perhaps is a way move forward. This is a challenge. There's no silver bullet to solve this problem.
Yeah, totally agree with you. Thank you. And for participants, if you have a question, you can pose it through the neural network platform. And my second question is, we all know that as ITU is committed to connecting the world, and no doubt connection is also a crucial topic in no matter human-robot collaboration, as well as in smart manufacturing. So how do you describe the relationship between artificial intelligence, information and communication technology, and smart manufacturing? Thank you.
Mm-hmm. Yeah, artificial intelligence or AI is being used every day by a majority of people. I guess the aim is to make systems smarter, no matter what system, what decision-making module. AI can help from that perspective, analyze the data, retrieve a pattern, make a better decision. However, many of machines, humans, are in a distributed environment and not centrally controlled by one computer. If that's the case, definitely that's a communication issue. the communication issue is once we retrieve data, we need to send from the sensor controller to another processing unit, another PC, or to a cloud server. If there's a real-time constraint, how to reduce the transmission time becomes critical. We have a pilot project in-house is try to use a 5G communication to improve the efficiency. But we are not in the communication field, not quite sure, but that could perhaps the ITU can contribute through better standard, better protocol for data communication, especially for applications with a real-time constraint. This is quite crucial. Eventually, both the communication, the AI algorithm is contributed to smart manufacturing. Smart manufacturing cannot be done offline, cannot be done in a slow pace. So that all can be put together in a complete picture.
Yeah, thank you. And another question is, as you mentioned, standards for human robotic collaboration safety issue. And so from the perspective of technical standards development, what do you think we can do to accelerate the development and application of AI techniques, AI systems in the smart manufacturing industry? Thank you.
Yeah, standardization. Yeah, my observations through my involvement in the past with ISO is the ISO standard considers the worst case, as mentioned in the last part of the presentation. Sometimes makes the standard very difficult to be applied. Like the robot needed to be safe, then robot has to move in low speed. In order to reduce the impact, robot speed reduced, impact is low. And also you can use your arm to stop robot. That means the force has a limitation. This is applied to collaborative robots, but not for conventional robots. Otherwise, if you apply force limitation, most of the robot becomes weak, cannot lift the heavy workload, not practical. So that's the issue. If it's for communication, for artificial intelligence, there's a similar concerns. How to make a new standard physical, practical is an issue. I also heard people talking about the ethical issues of applying AI. Perhaps that also worth attention from all of us, whether AI can be used for good or is AI for bad. That's things related to ethics we need to consider. Luckily, this webinar series, AI for Good, is moving to the right direction.
Okay, thank you.
I think ITU colleagues and other standardization organizations need to consider this issue and how to make a standard, new standard, feasible, practical.
Yeah, we can work for this collaboratively. Okay. Thanks, Professor Wang. That seems there are some questions from the audience, and from Reinhard Scarrow, and he asked if AI used in 3D printing.
Is AI used in 3D printing?
Yeah,
it can be used. Because we also have some research on 3D printing, particularly we use for 4D printing. In 4D printing case, we need to design the workpiece in the time axis, along the time axis. So the functionality, property of a material, as well as the shape and so on, need to be controlled over time, but everything needed to be done during the design stage. If just based on our current design principle, it is not possible to predict every cases. And if we use a digital twin combined with some AI algorithm, we can try different what-if scenario to make sure that the design and the printing is according to the specification. So I'm pretty sure the AI can play a role there as well. So this need also to be combined with big data from the environment. AI can retrieve pattern from big data and to help us to control the behavior of 3D printed or 4D printed product in the future.
Okay. Thank you again. And so thank you very much, Professor Wang. I would like also to thank the audience for attending this webinar session and listening to the fantastic speaker. We encourage you to check out the AI for Good program online to see more sessions that may be of interest to you. Actually, in November, we'll have another webinar on AI for manufacturing track, industrial AI for worry-free manufacturing, which will be presented by Professor Jie Li from the University of Cincinnati, United States. We are very much looking forward to engaging you in our upcoming events. Okay, now I'll give the floor back to Anna. Thank you, and bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. After the networking session, we invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.